Hi, this is Miss Litton. It is Friday afternoon, and we are reviewing Chapter 6, Energy and Enzymes. Say hi.
Hi.
Excellent. All right, so the first thing we need to know about energy is that they're just different kinds of energy. So there's energy of motion, that would be kinetic energy, right? There's thermal energy, heat. But the one thing we know for sure about energy is that energy cannot be what? Created or destroyed. It can just change hands, right? So all the energy in the universe is already out there. Okay, it's just how it's going to be manipulated. Every time it changes forms, then you're going to lose some as what? Heat. It's not always, doesn't have 100% change. You always lose a little bit as heat. The other thing we know is energy is starting as being useful, and then it's becoming less and less and less useful. And a measure of that disorganization is called what? Entropy. Everything is going to greater entropy, from most organized to least organized, from most useful to least useful. Now, the process of the sun going to greater entropy is good for us, because as the sun releases its energy as it breaks down, we capture its breakdown and use it to build things like plants, right? And then you and I can eat the plants and break those down and use that for energy. But overall, everything is going to less and less useful energy, and entropy is increasing. The thing about this high entropy situation is it's very stable, because once everything is broken down, right, then it's stable. It's probably not going to change much once it's broken down. But if you build something, right, a nice clean kitchen, low entropy situation, you run the risk of it getting messy, right? So we constantly have to input energy in order to fight entropy. You and I have to have a constant source of ATP, and we get that from breathing oxygen and eating food. It gives us enough ATP to fight our entropy so we can maintain what? Homeostasis. Perfect. So that's kind of your big picture there on energy. Then we looked at a couple scenarios, right? We said a solid would be low entropy, a liquid would be higher, and a gas would still be higher. I'm not saying that gases can't be useful, right? Hot steam, right, can cook broccoli, right? So that's very useful. But once that heat has dissipated, we can't do anything from it, right? Once it's spread out, we can't do anything with it. When we look at something like glucose, glucose itself is very low entropy. It's very organized. All those carbon and hydrogen and oxygen atoms all bound together. When we break it down and release the energy out, as we increase entropy from glucose, as we increase the entropy, as we break those bonds, that energy is released, and we can use it to build what? It's sugar. Why do we eat sugars? We want to build what? ATP. It's a coupled reaction, right? So as the sugar breaks down, we use this energy to go from ADP plus inorganic phosphate, and we use that energy to build ATP. Is it 100% efficient? No, it's only about 39% efficient with oxygen. Okay? That would be a coupled reaction. We're coupling the degradation of glucose with the building of ATP. Okay? Another example we looked at was looking at an unequal distribution of a substance across a membrane, just like water behind a dam. Water behind a dam can do work. Water the same level on either side of a dam can't do squat, right? But if you have more on one side, you can do something with that. So in this case, we have more hydrogen ions on one side, so we have a difference in concentration. We also have a difference in charge, because what's the charge on a hydrogen atom? Positive. And we have a difference in pH, right? Wherever you have a bunch of hydrogen ions, you have a low pH. So we can harvest this difference to do some work. And when we allow hydrogens to cross a membrane, if it goes through the right channel, or enzymatic protein, one called ATP synthase complex, when the hydrogens go through, it turns a turnstile in order to generate ATP. So that can be very useful, okay? So here, we're going to couple this energy, ultimately, to make ATP. You all right with that? Okay. Then we talked about metabolism. The metabolism of our body is the sum total of all the reactions that are catabolic, which break things down, and anabolic, which build things. And every one of those reactions, oh, thank you. Every one of those reactions requires an enzyme, both catabolic and anabolic reactions. The other thing we want to remember is the difference between reactants and products. Reactants is what you what? How would you describe a reactant? They participate. It's what you start with. And a product is what you what? End up with. Perfect. Okay? And so we took a look at this picture right here, which showed something breaking down. And in the process of breaking down, you're going to release energy out of the bonds, right? Because energy is just electrons. Electrons are energy. So when you break bonds, energy comes out. You can use that energy for anabolic processes. That's a coupled reaction. One thing releases energy, one thing requires energy. It minimizes waste. You work on it together, right? I'll spend money, you'll take the money, right? It's just a transfer. When you look, we already did reactants and products. When you look at the change of energy, right? If I am writing a bunch of checks and paying a bunch of bills, my checking account's going to go what? Negative. It's going to go down. My delta G will be negative. If I start putting in a bunch of checks and depositing, my delta G will be positive. I'll have more G's, right? So when we measure energy, it's like measuring a bank account. If you have a lot of money in your bank account and less money in your bank account at the end of a reaction, that delta G is what? Negative. If you have a little money in your bank account and a lot of money afterwards, that delta G is what? Positive. What do you think is easier, to spend your money or save your money? That's right. So there are little hurdles, little spending limits to prevent that. And those are little hurdles right here. And we learned what that little hurdle was. Do you remember what that little hurdle is called? Energy of activation. Remember that with enzymes? And so that little hurdle prevents us from spending money. If somebody took my debit cards, they could just wreck me, right? What prevents them from using my debit card? They have to know my what? My PIN. If they don't know my PIN, it's going to prevent that. Could they keep guessing randomly until they got my PIN? Sure. Could they eventually get it? Yeah. But I will put in my PIN 10 million times faster, right, than they can guess my PIN. Does that make sense? And that's what enzymes do. Enzymes lower that little hurdle to make this reaction, which is usually pretty easy, spending money is easy, to allow that reaction to go forward. All the energy change is there. I have more money in my bank account. It is a positive value. As soon as I start spending, it's going to go down, right? The PIN is going to allow me to do that. The enzyme lowers the hurdle so I can spend that money. Okay? If you are having an action that releases money, releases the money, exergonic, your money is exiting from you. If you are putting money in your bank account, that's endergonic. You're putting it in your bank and you're accruing energy. Got the difference? Okay. What prevents endergonic reactions from happening? Well, it's an input of energy. It's going to take effort to make your account. Could your account randomly just all of a sudden increase? Maybe. Maybe you win the lottery. Okay. But what are the odds of you winning the lottery? About 1 in 10 million. Right? So chances are it's not going to increase, right? We have to put something in to make it increase. We have to put that energy in. So then we talked about what is that money? What is the currency of our body? And that is ATP. Okay? ATP is our currency. And we said, let's look at the structure of ATP. ATP is an example of a nucleic acid because it has a base, in this case adenine, which is a purine. And it has a sugar, which is ribose, and it has a phosphate, and a phosphate, and a phosphate. And those two bonus phosphates, there's a lot of energy in those bonds. And so when you break off this bond right here, when you snap off this phosphate, here it is. This phosphate is this phosphate right here. Then you're down to ADP. But the bond that was here between this phosphate and this phosphate, this is equivalent to energy. And that energy allows you to do reactions. Notice what kind of reaction is this? What is that called? Hydrolysis. Hydrolysis. You're using water to lyse that, right? Is that going to require an enzyme too? Yeah, sure it is. All right. So then we looked at coupled reactions. We said if C and D want to go to being A and B, it must require energy because here's ATP on the reactant side and ADP on the product side, yeah? So A and B must have more energy than C and D. Where did they get their energy from? ATP. We coupled it together. We coupled that reaction. So we looked at all the things you could use ATP for. You can use ATP for any anabolic reaction. Any kind of building, you will use ATP. For any kind of transport, you will use ATP. For any kind of movement, you will use ATP. How do you get your ATP How do you get your ATP back that you spent? By breaking down some other molecule. Because if you want to build something, you have to break something else, right? Does that make sense? If I want to build something, I have to break something else. So I'm going to break down glucose, and I'm going to use the energy to build ATP. And that's why we do cellular respiration. Okay, before I go any further, are there clarifying questions you want to ask me? Anything Shadowlands? You need the flashlight of wisdom? All right? Okay. So now let's see. We said here are the things you can use energy for. Building things, transport work. Yes. Okay. Then we brought it into metabolic pathways. This triggers this, triggers this, triggers this. And we know enzymes facilitate every single one of those reactions. And enzymes are very specific to the reaction they're going to assist. They're specific because they bind to a specific substrate, because their pieces match. Their puzzle pieces match. If you've ever done one of those ginormous, like 1,000-piece puzzles, you know, then you know that puzzle piece only fits in one spot, right? Unless it's one of those really annoying puzzle pieces where you have to look at the picture. But anyway, so there's only one puzzle piece. There's only one substrate that's going to bind completely to this active site in order to make this reaction go. Now, could there be an inhibitor who can bind a part of this active site? Sure. But this enzyme has one job, to break down whatever this substance is. When they're joined together, they're called enzyme, substrate, complex. And oftentimes the enzyme will change its shape momentarily to facilitate whatever reaction it is. Could be a catabolic reaction, it could be an anabolic reaction, but it'll change its shape momentarily. And that is called induced fit hypothesis. Meaning in order to facilitate it, my enzyme is going to change momentarily, release my product, and I'm good to go again and again and again. That's why you only need a very little bit of enzyme, because it does not get consumed by the process. It can be reused again and again and again. So we talked about the hurdle. Without an enzyme, the hurdle is too big. You can try to figure out my PIN and put that in there at my bank and try and try and try and try and try. Could you get it? Maybe, but statistically probably not. But with my PIN, it lowers that hurdle and it's more likely to pull money out of my bank account. And it facilitates that process. Is it a specific bank? Yes. Is it a specific PIN? Yes. A specific card? Yes. Okay? All of those to that one particular reaction. And then, let's see who that was, did you? Okay. So then we said, well, what are all the things that can affect enzymes? What are the things that can impact that reaction? Well, one of those things is how much substrate you have. If you have a lot of substrate, then you're going to get a lot of product. That just makes sense. If I have a lot of reactant, I'm going to get a lot of product. So as you increase the substrate concentration, you'll increase the amount of product you get. At some point, you level off, though. and you level off because all the enzyme you have is working as fast as it can. All of its active sites are filled, so you're not going to change anything there. The only way to make this reaction go faster would be to do what? Add more. Well, you could add heat, sure. You could add heat. What else could I do? Add more enzyme. Yeah. Heat will make any reaction go faster, but more enzyme will make that specific reaction go faster. So we did look at temperature. So temperature, each enzyme has a specific temperature because in that temperature it has just the right shape. Where do we keep Jell-O? Refrigerator. If you have a Jell-O mold you made for Thanksgiving, it's a giant cornucopia that you made with your Jell-O mold. You let it sit out, what's going to happen to it? It's going to melt. So its optimum temperature for the Jell-O mold has to be in the refrigerator. If you put it on the stove or next to the turkey, it might melt. So there's an optimal temperature for each enzyme to facilitate the way it works. And any heat at all will make a reaction go faster up to a point. And that point is the point when you do what to the protein of the enzyme? Denature it. Exactly. Once you denature it, it drops off dramatically. We also looked at pH, and pH has the least amount of wiggle room. Most enzymes have a very specific pH they work at, and you don't want to change that at all. And keep in mind, changing 1 degree temperature is not the same as changing 1 pH unit, because each pH unit is really what? 10 degrees, right? So it would be like going from 60 to 80 degrees, right? From 80 to 90 degrees when you change pH, because it's a tenfold. Actually, that would be like 80 to 100, right? Because each time is 10 times. Okay, I'm going to keep with that analogy. Then we talked about coenzymes. I don't think I talked to you about cofactors, did I? I mean, I might have mentioned it, but anyway. Cofactors are like pieces of metal, like inorganic metal. But coenzymes are an organic. Maybe it's something not a protein. Otherwise, if it was a protein, it would just be part of the enzyme. So it's different. It's some sugar, some vitamin, some lipid that makes that enzyme function. And if you don't have that coenzyme, then it doesn't matter, the enzyme won't work. That coenzyme will make sure the active site is ready to go for use. So it facilitates making the active site correct. And then we talked about inhibition. We said, well, there's a couple ways. You can inhibit it directly by binding to where the substrate is supposed to bind. I know I'm speaking fast. Are you okay? I'm just trying to hit everything as fast as I can in the simplest of terms, but you're all right? Okay. They're nodding. Just in case you're wondering, they are nodding. You're not here, so you don't know that. Okay. We are eating like vanilla lattes with ice cream and chocolate chip cookies, but you're not here. I brought them in today. Aren't they delicious? Yeah. And we just finished pizza. It was super good. Yeah, we had pizza. What else did we eat? We had chocolate. We also had a whole bunch of Flaming Hot Cheetos and Doritos and French fries with ranch dressing, in case you're wondering. That's what we're eating right now. Okay, now, that enzyme has an active site, and if something goes and binds to that active site, that's competitive inhibition, because it's competing with the substrate for the active site. Non-competitive inhibition is just as effective. It's just binding somewhere else on the enzyme, which messes up the active site. It's just two ways to shut that enzyme down. Two different ways. Either totally get in the way, that's competitive, bind to another part and mess with the active site as a result. That is non-competitive inhibition. And then we talked about end product inhibition, where in this case, the end product is the thing that's going to bind to that allosteric site and be a non-competitive inhibitor. But that's a good thing, because if we have enough of that product, we don't want any more. So when we have enough, it shuts down the very first enzyme, so we stop the whole process at the very beginning of the metabolic pathway, not at the end. So that way we don't waste any energy. All right. Now, switching gears. We talked about being reduced and oxidized. And when we did that, that was just a way to tell the level of energy that you're at. And it's counterintuitive, right? Because when we hear the word reduced, we think low. But what that really is referring to is that you have a low what? What's low when you're reduced? Reduced in charge, because electrons equal energy. And you know electrons have a negative charge, just like protons have a positive charge. So if you gain electrons, you're going to gain energy. And because electrons have a negative charge, you say it's reduced. So it is reduced in charge, but it's it's very powerful in energy, okay? And if I hand off, if my glasses are electrons and I hand them off, he now has my electrons, he's reduced, and I would be referred to as what? Oxidized. I've lost energy, he's gained energy. And we talked about different ways that can happen. We said, I can gain electrons, I'll be reduced. I can gain energy, I'll be reduced. If you hook me up with hydrogen, I'll be reduced. And why is that, bless you? Because hydrogen tends to what? Give its electrons. And the last way you can reduce me is to break me away from somebody, to get rid of somebody, to pull them away from me. Who is that you want to pull away? Oxygen, because oxygen's a taker, right? So to reduce me, I need to gain electrons, gain energy, gain hydrogen, or break up with oxygen. Conversely, if you want to lose energy, you could lose electrons, lose energy, you could hook up with oxygen, who will take your energy from you, or break up with hydrogen, who would have given you energy. Remember we talked about like hydrogen being our good friend who's encouraging to us, whereas oxygen is that drama friend who always takes things from us. Okay. We did this right here. You remember this? Okay. And then we brought it full circle. And we learned about energy and enzymes and reduced and oxidized. Also, we could talk about cellular respiration and photosynthesis. And the chloroplast does photosynthesis. It builds carbohydrates. What does it need to build those carbohydrates with? It needs sunlight, right? It needs sunlight. What else does it need? CO2 and water. It needs CO2 and water to build those carbohydrates. Okay? And then mitochondria, they need those carbohydrates, but if they want to do it the most efficiently, they need oxygen. And it's really nice because the process of photosynthesis does generate oxygen, right? So we're going to use that oxygen, use those sugars in order to build ATP. And then we give off CO2 and water that the plants can use. So this just goes round and round. And we talked about this right here and about identifying what gets reduced and what gets oxidized. So if I just draw this arrow right here, just that arrow, I'm starting off, and this way I'm doing photosynthesis, right? This way is photosynthesis. I have CO2, now I have this. What's different with the CO2? How has it changed? It gained hydrogen. So what happened to it? It got what? Reduced. Who gave it the power to reduce? Energy from the sun. I don't know what I'm spelling. Now it's even worse. Energy from the sun gave me the power to give them those hydrogens. Do you know where those hydrogens came from? From the water. From the water that got what? Oxidized. Okay? When we eat sugar, that sugar is going to become CO2. Right? And so what happened to the sugar? It got oxidized. It got oxidized, and we removed those hydrogens. Who did we give the hydrogens to? We gave these hydrogens to who? Oxygen to become what? Water. And in the process of breaking these bonds right here in the glucose, we were able to make energy. Well, not make energy, because energy is neither created nor destroyed. But we could transfer it into what? ATP. Okay, and then we revisited this idea right here, that membrane and that differential. And basically what we said is, if you can concentrate hydrogen ions, on one side of a membrane, okay, then you will create a difference in concentration a difference in charge, a difference in pH. And these hydrogen ions will want to come through something called ATP synthase complex in order to make ATP, because they will want to go from a higher concentration to a lower concentration. So now the question is, how'd you get those hydrogens to be on that side so you could make that ATP? Well, we gave some proteins some energy. Where did we get them from? Bonds. And we do what's called an electron transport chain, where I take high energy electrons, I pass it to one receptor who's also, and they will take these hydrogen ions and they will move them from one side to the other side. And then they'll pass that energy along, and it will still be able to use that energy. There's still useful energy. And they will concentrate hydrogen ions to one side of the membrane. And when we're done, we have to have somebody take the final handoff of that energy. And when they do, then we can keep this cycle going, so we can keep concentrating hydrogen ions on one side, so when they go back across, we make ATP. Okay, got that? Do you want to take a practice quiz? Okay, so I hope you are having a good weekend, and it's not super late on Sunday night when you're finally listening to this. I hope it's earlier, and if you get hungry, have a piece of toast. Much love. Make good choices. Don't stay up too late.